Neutron diffraction. Neutron diffraction is a technique used for crystal structure determination. First, we must have a clarity or clear idea about the phenomenon diffraction. Diffraction is spreading or bending of waves or stream of light or sound exhibiting wave nature around the corners of an obstacle which is present in that path. This spreading is occurring into the region of shadow of the obstacle and is accompanied by interference of waveforms. Therefore, for the diffraction to be observed, we essentially need a stream of light waves or sound waves or a stream of particles which could behave as waves. In the present study, that is neutron diffraction, a stream of neutrons behaves like a wave and also can be diffracted by materials present in the wave. Neutron diffraction is the scattering of neutrons by matter, and that scattering will produce a diffraction pattern which is similar to that obtained for X-ray diffraction. From these diffraction patterns, the positions of atoms and thereby crystal structure can be inferred. In determining crystal structures, neutron diffraction is complementary to X-ray diffraction. Beam of neutrons behaves like a wave. Hence, we have to produce a beam of neutrons. Generally, neutrons are produced by nuclear fission reactions in atomic piles. Thus formed neutrons are high energy neutrons. We have to reduce their energy by using moderators. Then we have to produce a monochromatic neutron beam by making use of a velocity selector device for the study, diffraction study. Neutrons can also be produced in several other nuclear reactions. Two such reactions are bombardment of beryllium nuclei by alpha particles and bombardment of sodium nuclei by gamma radiation. Both these nuclear reactions produce neutrons. Then, theory of neutron diffraction. That is, how do diffraction of neutrons by crystals is possible? This can be understood by the following discussion. According to de Broglie equation, the wavelength lambda equal to h by mv, where h is Planck's constant, m mass of neutrons, v velocity of neutrons. Then kinetic energy of neutrons is given by the equation half mv square equal to 3 by 2 kT, where k is Boltzmann constant, T is temperature. From this equation for kinetic energy, we can arrive at the equation for momentum, that is mv, which is equal to square root of 3m kt. On substituting this momentum in the equation for wavelength, we can rewrite the equation for wavelength as lambda equal to h by square root of 3m kt. Substitute the values of various parameters in the equation for wavelength. On manipulating the equation, it is arrived at as the value of lambda as 1.46 angstrom units. This value is of the order of bond lengths, that is spacings in crystals. This is the reason for the fact that beam of neutrons is suitable for diffraction study of crystals. That is, the wavelength must be of the order of distance between atoms or ions present in crystals. This is an essential condition for the diffraction to occur. Then detectors. We have to record the diffracted neutrons. From the diffraction pattern, we can infer the structure of crystals. In the case of X-ray diffraction, we can make use of photographic plate. But neutrons are not affected, not detected by photographic plates. So we have to make use of counters which are shielded against radiation. In neutron spectrometer, the detector is a boron trifluoride counter. Another condition is the boron in this boron trifluoride must be enriched with the heavier isotope of boron, that is B10, because with the B9 the efficiency of the counter is very less. Then origin of neutron diffraction. The diffraction of neutrons is caused by nuclear scattering and magnetic scattering. Nuclear scattering occurs when neutrons interact with the nuclear particles, namely protons or neutrons. Whereas magnetic scattering is the result of interaction of magnetic moment of neutrons with the permanent magnetic moments of atoms or ions concerned. We may wonder, how do neutrons, the neutral particles, electrically neutral particles, possess magnetic moment? Neutrons have spins. Because of that spin, neutrons have an intrinsic magnetic moment. This interaction is possible only with the substances having permanent magnetic moment. That is, they must possess some unpaired electrons. That is, they must be paramagnetic in nature. We can cite iron 3+ compounds as example for substances with a permanent magnetic moment. These two types of diffractions can be distinguished by the fact that neutron waves are polarized by magnetic scattering and not polarized by nuclear scattering. Now let us see the two types of scatterings in detail. First, let us take nuclear scattering. Nuclear scattering depends upon nuclear size and nuclear structure, and it is because of the interaction between the neutrons and the atomic particles. So, neutrons have to penetrate the atoms, they have to go well inside the atom to meet the nuclear particles. This is possible because the penetrating power of neutrons is very high. In the case of X-ray diffraction, their penetrating power is not so high as that of neutrons, and that is also not needed in X-ray diffraction because they are interacting only with the outer electrons present in the outer surface of atoms. The scattering center of neutrons in nuclear scattering is the atoms, the atomic nucleus. Even a small hydrogen atom scatters neutrons, and this scattering is as good as that done by potassium. Then the capacity of an atom to scatter neutron is denoted by the term neutron scattering factor. It is nothing but the ratio of scattering power of an atom to that of a single electron. This neutron scattering factor for lead is 3.41, while that for oxygen is 2.11. Since lead nucleus is bigger than oxygen nucleus, it has greater neutron scattering power. The nuclear scattering factor is a function of atomic number, but they do not vary directly with the atomic number. And another point is these nuclear scattering factors have no dependence on scattering angle. The next one is magnetic scattering. In magnetic scattering, the scattering centers are electrons. This magnetic scattering is possible in the case of substances with permanent magnetic moment. In the case of substances with a permanent magnetic moment, two types of scatterings we could observe. That is nuclear scattering as well as magnetic scattering. Now, advantages of neutron diffraction exclusively due to magnetic scattering. Neutron diffraction, the first advantage is it can experimentally distinguish ferromagnetic and antiferromagnetic crystal structures. In ferromagnetic substances, the moments of neighboring atoms are arranged parallel, and in antiferromagnetic substances, the magnetic moments of two neighbors are opposite to each other. So, when neutron diffraction is performed, the diffraction pattern indicates the direction of alignment of spins within the crystal. Thereby, as a result, we can identify ferromagnetic and antiferromagnetic substances. Transition metals such as iron, cobalt and nickel are ferromagnetic substances, and transition metal salts such as Fe2O3 and MnF2 are examples for antiferromagnetic substances. These are some images of magnetic scattering that occurred during neutron diffraction. Another advantage of magnetic scattering is identification of intervalence compounds. A compound containing an element in two different oxidation states is known as an intervalence compound. For example, let us take Fe3O4. In this compound, one ion is divalent and the other two are trivalent. Actually, the formula is written as FeO, Fe2O3. In the species FeO, ion is present in divalent state, and in the species Fe2O3, ion is present in trivalent state. Actually, X-ray diffraction could not distinguish these two ion species, but this is possible with neutron diffraction because the two ions have different number of unpaired electrons and scatter neutrons differently, and hence these two have different magnetic scattering capacities. Then neutron diffraction is possible with the gaseous substances and liquid substances also. Here is a comparative account of X-ray diffraction and neutron diffraction. This is analyzed in four aspects. The first one is atomic scattering. In this aspect, in X-ray diffraction, it is an electronic phenomenon, whereas in neutron diffraction, it is nuclear phenomenon. In X-ray diffraction, scattering depends upon the angle theta, whereas in neutron diffraction, there is no angular dependent factor, that is, it is isotropic. In X-ray diffraction, the scattering power increases with the increase of atomic number. The increase is regular, whereas in neutron diffraction, there is no regular variation with the atomic number. Then, in X-ray diffraction, no difference is observed among isotopes, whereas in nuclear diffraction, the diffraction is different for different isotopes. The second aspect is magnetic scattering. In X-ray diffraction, no magnetic scattering is observed at all, whereas in neutron diffraction, with paramagnetic substances, magnetic diffraction is also observed along with the nuclear diffraction. Third view is absorption coefficient, which is very large in X-ray diffraction and very small in neutron diffraction. Then the fourth one is absolute intensity. That is, measurement of absolute intensity is very difficult with the X-ray diffraction and possible with the neutron diffraction. Now the final part of the presentation, that is applications of neutron diffraction. The first and foremost application is location of hydrogen, that is finding the location of hydrogen. The neutron diffraction is mainly used to study crystals whose structure are known except for the position of hydrogen atoms. When a compound contains a heavier atom like uranium and a lighter atom like hydrogen, then X-rays can locate only uranium and not hydrogen, because the scattering power of, that is X-ray scattering power of uranium is very high and that of hydrogen is very less. The scattering power of uranium overwhelms the scattering power of hydrogen. So it is not possible to find the location of hydrogen in a compound containing uranium and hydrogen. Whereas with the nuclear diffraction, we can identify the location of the hydrogen atom, because in the presence of heavier atom like uranium, because the neutron scattering power of hydrogen is somewhat high, which is as good as that done by potassium. Thus, in a compound such as UH3, X-ray diffraction is used to determine uranium coordinates and neutron diffraction is used to determine hydrogen coordinates. Similarly, in the structure of a lead oxide, the position of lead alone is indicated by X-ray diffraction and the position of oxygen is identified by neutron diffraction. Another important application is ascertaining the structure of ice. The structure has been established with the X-rays and neutron diffraction data. Other applications of neutron diffraction includes identification of water molecules in hydrates, identifying ferromagnetic and antiferromagnetic materials, and studying order-disorder transitions of alloys. The only drawback of neutron diffraction is the neutron sources are very expensive and are not readily available. Otherwise, neutron diffraction is a good tool for the study of structure of crystals, gaseous substances, liquid substances, and powder form of solid substances. Learning is a treasure. Develop a passion for learning. Thank you.